Starting with an theorem. The theorem states that if f be differentiable on an interval I, that is f from I to R be a differentiable real valued function, and C be any point belongs to I, that interval, that is the domain of the function, then f dash c greater than 0, this will imply f is an increasing function at the point x equals to c, and f dash c less than 0, this will imply f is decreasing at the point x equal to c. Okay, so this theorem is applicable for any differentiable function defined on an interval I. F dash c greater than 0 will imply it is increasing at that point, and it is less than 0, this will imply this is decreasing at that point. Now we will use this theorem to solve a few examples. So the first example is fx equals x cube plus 2x plus 3, where x belongs to R. Then show that f has an inverse function g on R, and find g dashed at the point x equal to 0 and x equals to minus 1. Okay, this is the function fx given. First we have to show it has an inverse function g on R. Now we have already known what are the criteria of the existence of inverse function or inverse differentiable function. The criteria are it should be a monotone function, it should be continuous, differentiable, and f dash x should be not equal to 0, right? So at first check for the monotonicity part. Monotonicity part, this is a polynomial, so and it is a function, real valued function x cube plus 2x plus 3. So we can apply this previous theorem. So at first find out f dash x. F dash x is 3x square plus 2, right? Now check whenever x belongs to R, if you take any positive number, x square is positive. If you take any negative number, x square is still positive. Then 3 into some positive quantity, it is positive, plus 2, the whole thing becomes always positive, whatever value you take for x. So this f dash x should always greater than 0 for all x belongs to real number system. That means it lies in the first criteria of our previous theorem. That is, whenever f dash c greater than 0, the function is increasing. So from here we can claim that the function f is monotonic increasing. Okay. So the first criteria of the existence of inverse function is satisfied. Next is continuity and differentiability part, this and this part. So for that reason we know that f is a polynomial, x cube plus 2x plus 3. So polynomial, it is always continuous and differentiable. So the second, third condition is also satisfied. Next one is f dash x should be not equal to 0. Now f dash x is 3x square plus 2. If you put this equals 0, what will happen? You will get x square equals minus 2 by 3, right? Which is not possible over R, because otherwise it will become a complex number. So f dash x is always not equal to 0 over real number system R. Okay, so all the conditions are satisfied. So we can claim that f has an inverse function g, and the derivative of that inverse function, that is g dashed, also exists. And we know the rule. The rule is g dashed y will be 1 by f dashed x. Where what is y? Y is the functional value at the point x, that is y equals fx, right? Now we will use this rule to get the value of g dashed at the point given in the question, at the point x equal to 0 and x equal to 1. Now whenever x equal to 0, what will be the value of 1? F of 0? F of 0 will be, if you put x equals 0 in f, you will get 3. And f of minus 1, if you put it, you will get minus 1 minus 2 plus 3, that is 0, right? So g dashed 3 will be equal to 1 by f dashed 0. Now what will be f dashed 0? F dashed value is 3x square plus 2. Now put it x equal to 0 over there, you will get 1 by 2. So the result is 1 by 2. Okay. Similarly, if we want to calculate g dashed of 0 then it will be 1 by f dashed minus 1, right? Now what will be its value? It will be 3 into minus 1 its whole square plus 2, that is 5. So 1 by 5. Okay. This is how we get the value of the inverse differentiable function. Now I am giving you another example, just similar example as your homework. Okay. Write down next example. Fx equals x to the power 5 plus 3x cube plus x plus 4 over r. Find g dashed, find g dashed at x equals 1. Find g dashed at x equals 1, where g dashed is the inverse differentiable function of f. Inverse differentiable function of f. Okay. Just by applying similar method, you have to solve this. Solve it. Okay. Next, moving to few more examples. Write down. A function f is defined on some neighborhood of C and it is differentiable at C. A function f is differentiable at C. Then prove that limit h tending to 0, f of c plus h minus f of c minus h whole divided by 2h equals f dashed c. Then prove that limit h tending to 0, f of c plus h minus f of c minus h whole divided by 2h equals f dashed c. Okay, that means we have to show the limit of that whole function when h tending to 0 is equals to this, right? That means if we can show that the limit of this function, the left hand limit and the right hand limit of this function are same and it is take the value f dashed c, then our work will be done. So we are starting with right hand limit. Limit h tending to 0 plus. Let's check its value. We are adding f of plus minus c over there. So minus fc plus fc. Okay. This. Now writing it like this. Taking this part plus this part. So it will become f of c plus h minus fc divided by h. And there was one 2. I'm taking it common over there. So half. Half into limit this one plus limit h tending to 0 fc minus f of c minus h by h, right? Not actually 0, these are all 0 plus. Okay, now check this part. What will be its value? According to the definition of differentiability, it will be the right hand limit of f dashed c, as there is 0 plus. So we can write this part as half of right hand limit of f dashed c. We are writing it as r f dashed c. Okay. And for this part we cannot say anything. So for here we are putting h equals minus k. Okay. So if we put it, what will we get? Limit when h tending to 0 plus. If you put h equals minus k, then k will be tending to 0 minus. So it will become k tending to 0 minus f of c plus k minus fc divided by k, right? Just you put minus k over there, then this minus will become plus, and this will become c plus k, and this is minus c, minus f of c. So this one. Now from this part, what we can conclude? This is actually the left hand limit of f dash c according to the definition of differentiability. So we can write it as plus half of, there is obviously 1/2 there, so half of L of f dash c. Now half of right of f dash c and left of f dash c, that means ultimately f dash c. Okay, so we got that the right hand limit of the given function is f dash c. Similarly we can show that limit h tending to 0 minus this whole function f of c plus h minus f of c minus h whole divided by 2h, its left hand limit is also f dash c, right? That means the left hand limit and the right hand limit both are same, and it's take the same value f dash c. So this is the limiting value of the function. Okay. Next, moving to the next example. A function f from R to R is defined by f0 equals 0 and fx equals 0 if x is irrational, that is x belongs to q complement, and this is equals 1 by q if x is rational. Fx defined like this. Then show that f is not differentiable at 0. Then show that f is not differentiable at 0. This is the question. We have to prove it. Okay, we will use, here we have to prove f is not differentiable, right? That means we have to disprove something. So for disproving the sequential criteria of differentiability, this is very important, so we will use it here. It is given the function is from R to R and the value of the function is taking like this. This is for irrational, this is for rational, and for 0 it is taking f0 equals 0. Then we have to show f is not differentiable at 0. Now what will be the definition of the differentiability at the point 0? At any point x equal to c, the condition is fx minus fc by x minus c. When limit extending to c, it should exist, finitely exist, right? Then we will say at the point c, the function is differentiable. Now here we have to check at 0. So we are considering this limit. Limit extending to 0, fx minus f0 by x minus 0, right? What will be its value? This f0, 0, so it will become fx by x. Now we are naming this limit as phi x. This function, not actually limit, as phi x. And let's check the phi x, limit extending to 0, phi x exists or not, right? If it exists, then we will say it is differentiable at x equal to 0, this function fx, and if it is does not exist, then we will say it is not differentiable at the point x equal to 0. So here we are choosing phi x equals fx by x. Now, at first we are choosing a sequence xn equals this sequence 1 by n. Then it's a sequence of rational number, right? 1 by n, where n belongs to natural number. That means it's a sequence of rational number. Then what will be phi of xn? Phi means fx by x, right? So it will be phi of 1 by n. That means f of 1 by n by 1 by n, that is n into f of 1 by n. And what about limit n tending to infinity phi of xn? It will become limit n tending to infinity so n into 1 by n, right? That means the limit is equals to 1. So xn, we got the sequence xn. This is tending to xn means 1 by n. That means xn tending to 0 and phi of xn is tending to 1. Okay, this one. Similarly, we are considering another sequence yn and taking it as suppose root 2 by n. Okay, then this is obviously a sequence of irrational numbers. Right, and the limit of yn is tending to obviously 0 as n tending to infinity. And what about phi of yn? Phi of yn means f of yn by n, by x actually, f of yn by yn. Then after getting the limit for fx, when x is irrational, that is root 2 by n obviously irrational, then it is going to 0. That means phi of yn will tending to 0. This one. So we get total two sequences xn and yn, both converging to 0. But the sequences phi of xn and phi of yn, they are not converging to the same number. They are converging to two different limits. That means the limit does not exist. Limit doesn't exist. That means f is not differentiable. Okay. Moving to the next example. The next example is let f of x plus y equals fx plus fy for all x comma y belongs to R. F of x plus y equals fx plus fy for all x comma y belongs to R. Prove that if f is derivable at one point of R, prove that if f is derivable at one point of R, then it is derivable throughout R. Then it is derivable throughout R. Okay, we have to prove it. It is given only one rule for the function f, that f of x plus y equals fx plus fy for all xy belongs to R. And it is also given that if it is derivable at one point, that is some point, suppose C, at one point C of R, then it is derivable throughout R. That means this one point differentiability is implying the differentiability throughout the real number line. So let's take it is differentiable at the point C. Solution: let f is differentiable at C belongs to R. Then what will be the value of f dash C? it will be limit h tending to 0, f of c plus h minus fc by h, right? Now what will be the value of f of c plus h according to the given rule in the question? It will be fc plus fh minus fc by h. fc and fc will be cancelled out, so it will become h tending to 0 fh by h, right? So this value, limit h tending to 0 fh by h, this limiting value is equal to f dash c, keeping it as equation number 1. Okay, now we have to prove f is differentiable throughout R. That means we will choose any arbitrary real number other than c, obviously. Then we have to prove this is also differentiable at that point. So let p be any arbitrary real number other than c. Okay, then what will be its value? Then we are starting with limit h tending to 0. We are trying to show that the function is differentiable at the point p. So we are starting with the limit h tending to 0 f of p plus h minus fp by h. Okay, if we can show this limit exists, then we can say that the function is differentiable at the point p. So what will be the value of this limit? F of p plus h, that means fp plus fh minus fp by h. fp cancelled out, it will become fh by h, and by 1, equation number 1, we got that its value is equal to f dash c, right, by equation 1. So the limit, this limit exists finitely. This limit h tending to 0 f of p plus h minus fp by h, this limiting value exists finitely and its value is f dash c. So the function is differentiable at the point p, and p was arbitrary, so the function is differentiable throughout the real number line. So f is differentiable throughout R. Okay.